Hello and welcome everyone. So I'm back again with the another solution for problem of the day. My name is Dalsaniya and how are you guys doing? Hello, hi Rishit. Okay, so we'll be discussing today's problem of the day, but before moving on to the solution part and the further, so I would like to know if I'm clearly audible as well as visible or not. I guess I'm clearly visible and as well as audible. Hi, hi everyone. कैसे हो आप लोग? So how was your today's problem of the day? Today's problem of the day was kind of very much interview centric. Okay, so this entire month contains all the questions that are going to be interview centric, right? And hence the problem of the day was as well. So I'll be sharing today's sharing my screen and then we'll be starting the session. Okay, I hope my screen is visible to everyone. Okay, so today's problem of the day, the name of the question is right view of a binary tree. Okay, so this question asks you, like, basically in this question you have to find the right view of the binary tree. Okay, so there are many different variations of this question available. So there are questions that will ask you to find the left view of the binary tree. Some of the question will like there's a question to find the top view. You can find the bottom view of the binary tree and much more, right? So basically, this is one of the view that is the right view of the binary tree. And what is the right view of the binary tree? Let's say this is the binary tree given to us 1, 2, 3, 4, 5, 6, 7, and let's say 8 is over here. So this is a binary tree. And if I'm currently standing at this point, if I'm currently standing at this point, and if I take a look at this binary tree, which all nodes are visible from this side, from this is the right hand side, right? So from this side I can see node number 1, 3, 7, and I will also be able to observe this node, right? So 1, 3, 7, and 8 are the nodes visible from the right hand side of the binary tree, right? Is it correct? Yes or no in the chat box. This is what I'll be able to observe, right? So basically in this question you have to for the given binary tree you have to find out its right view. Okay, so what you have to do, you have to find out all the nodes that will be visible from the right hand side, and what you have to do, you have to add all those elements in a list or an array list depending upon which data structure is given to you in your specific programming language, right? So over here, let's say I am coding in Java, and in Java you have to list down all the nodes in an array list. Okay, so I'll be storing 1, 3, 7, and 8, and this array list will be returned by the function in which you will be writing your entire algorithm, and that function is right view. Okay, so this will be returning a list, and in the output all the elements will be printed in sequence starting from zeroth index. So basically that is what the driver code will handle, right? So now how to solve this question? This question is not that much difficult. Basic traversal technique is required, right? So if you know how to traverse the binary tree, there are basically two different ways. One is level order traversal and another one is the depth first search, BFS or DFS, right? Only two traversal techniques are famous among graph and trees. Is it so? Yes or no in the chat box? Every question, whether it is from graph or whether it is from binary trees or tree data structure, everything revolves around DFS and BFS. Okay, so these two algorithms rule the world of DSA, BFS and DFS. Okay, so how to solve this question? So anyone from the audience would like to share me any of the approach? Okay, so basically, if you are aware about the levels of a binary tree, then I can consider this as my level 0, level 1, level 2, and level 3, right? And if you know how to apply breadth first search algorithm, that is a simple breadth first traversal, that means traversing level wise, that is level order traversal, then it will be very easy to find uh, the right nodes, right? Then it will be very easy to find the nodes of the right view. So basically, if I apply breadth first search algorithm for BFS or level order traversal, I'll be needing a queue data structure, right? And how will this work? I'm just giving you a basic idea about the brute force approach. Yes, basically for each and every level, you have to take the rightmost node. Okay, so how will this work? Let's try to implement it on this given binary tree. So initially, one will be present inside your uh, Q data structure, and what you will be doing. So currently, this is level 0. Okay, this is your level number 0. So you will be removing all the nodes of a particular level from the queue, and the last node which will be removed will be the part of your answer. That means that node will be visible from the right hand side. Okay, so currently this is level 0. So I'll be removing this node, and what I'll be doing, this is not the last node, right? So I'll be adding both its left and right child. So over here, I'll be adding first of all left and then the right. Yes, Q. So basically left and right, so 2 and 3 will be inserted, and this one will be removed from the queue. And this was the last element of our level, so it will be added to our list. Currently list is empty. Let's call it as answer list. So now removing the next element. So now this is an completely new level. This is a new level. So this is your level number 1. So removing all the elements one by one. So that would give me first of all, I'll be removing 2. 2 will be removed. And what I'll be doing, I'll be adding both its left and right child. So 4 and 5. So 4 and 5 will be inserted. And now 3 will be removed. And 3 has left child as 6 and 7. So 6 and 7 will be inserted. And which is the last node? 3 is the last node. So insert inside the answer list, right? So moving on forward with the next level. So the next level comes out to be level number 2. So over here, removing 4 left and right child, so it does not have any left. So 8 will be inserted, and for 5 nothing is there. For 6 no children. Over here you can observe for 7 no children, right? This is the last node which will be removed for this level number 2. Insert it inside your answer. Okay, so now our Q data structure contains only a single element. That element is of the last level. That element is of the last level. So this is currently our level number 3. 0, 1, 2, and 3. And I'll be removing 8 left, no child, right, no child. So this will be removed from the queue, and this is the last node of our level. So insert it inside the answer. And this is the entire right view of the binary tree. Okay, so this question is very easy. Just needed the level order traversal. Is it clear? Yes or no in the chat box quickly? If it is clear, then write down the what will be the time and space complexity as well. What do you think? What is the time and space complexity of this approach? So basically, whatever is the time and space complexity of level order traversal is going to be the time and space complexity of this approach. So for level order traversal, I need, what will be the time complexity? I'm iterating over the entire binary tree. So let's say n number of nodes are there, right? So time complexity will be order of n. What will be the space complexity? And what I'll be doing, I'll be considering that in worst case, all the n elements will be present inside our queue. Although that is not going to be true, because at in worst case, at max, whichever level has highest number of nodes, that many number of elements will be there inside your queue, right? So basically you can call it as the diameter of the binary tree. In worst case, whatever is the diameter, that many nodes can be possible inside your uh, this queue data structure. So let's say I'm calling it as order of n. Okay, so that means total number of nodes. So this is going to be our time and space complexity, right? So now can we optimize this further? So let's observe our approach number 1. I'm not coding this approach, because you simply need to know level order traversal in order to solve this question. Okay, so I am leaving this part for you guys, because you guys are smart enough. At least this can be expected from you. So now what about the optimization part? Okay, so time complexity, I don't think anyhow I can optimize the time complexity, because at least I need to traverse each and every node of the binary tree in order to find out which node will be visible from the right hand side, right? Because at each and every level you can observe there are a few nodes available. So let's say if I was traversing, and at some point I was currently standing at 4, so I cannot directly know that whether this node will be visible from the right hand side or not, right? So at least I need to traverse all the nodes of every level. Then only then I'll be able to figure it out whether this node, whether which node will be visible from the right hand side. So time complexity cannot be optimized, but let's say what about the space complexity? What do you think? What about the space complexity? Somehow I think I can solve this entire question without using Q data structure, right? I don't need to store anything inside any data structure in order to find out which node will be visible from the right hand side. So what I'll be doing? I'll be using a different kind of approach. That is basically I'll be traversing it in a level order manner, but using depth first search, or you can call it as uh, the recursive traversal. Okay, so we got a reply from Ramu. He says traverse right tree of the right child, right tree of the right child till left node, till the leaf node. Okay, so you are saying that I should keep on traversing the right hand side, right? So this won't work because over here you can observe, if I even though if I traverse till the leaf node in the rightwards direction, then this node will not be encountered, but this 8 is also the part of the right view, right? So I cannot simply go on traversing the right hand side. Okay, you were correct, but partially you were correct. So just a minute, I'll be sharing the screen again. So what else can we do? Anyone from the audience, what do you think? What can we do? Okay, so basically recursive approach will work totally fine. I agree with you guys, but uh, apart from it, how to apply recursive approach? Okay, so I'm just give me a minute. Okay, so let me clear this entire tree. What I'll be doing, I'll be traversing this entire binary tree. See, this is the observation part. Okay, so if I'm traversing this entire binary tree, let's say I'm traversing it in this manner, and this let's say this is, let's say first of all I'll be traversing the right node of the current tree. Basically I'll be doing the pre-order traversal D, R and L, but it is a little bit inverse of what we used to do. We used to traverse in root, left node and right node. So over here, as I'm looking forward to find the nodes of the right view, I'll be preferring moving in the rightwards direction each and every time. Okay, so I'll be traversing in this manner. That this is pre-order traversal, root node, right child and then the left child. Okay, so over here if you observe, this is level number 0. We know that there are some levels present inside this. So what I'll be doing, I'll be keeping the track of the maximum level till which I have traversed till now. Okay, I'll be keeping the track of the maximum level till what maximum level currently I have traversed. Okay, so that value will be stored inside my max variable, and one more value will be storing. This is DRL. In this manner I'll be traversing, and one more value, that is currently I am at which level. Currently if I am standing at any particular node, then what is the level of that node, at which level that node is present. Okay, so I'll be keeping these two values and then I'll be calculating. And I'll be traversing in this manner: pre-order traversal, root, then right child and the left child. Okay, so currently my level will be equivalent to, see, I am initializing the maximum level as 0. Okay, so at each and every time, whenever I reach a new level, whenever I traverse a new level, I'll be considering the node which I have encountered as the node which will be visible from the right hand side. So basically, whenever I'll be encountering a new level, whichever is the first node I'll be encountering, I'll be putting that node inside my answer, because I'm traversing in this manner, in the pre-order traversal, in which I'll be exploring the right subtree before exploring the left subtree. Okay, so currently my max level is equal to 0, and my what is my level? Currently I'm standing at level number 0. Let's say currently I'm standing at level number 0. So whenever I encounter a new level, my max level is going to be lesser than my current level. So whenever I encounter new level, so this keeps the track of the maximum level which I have encountered, and this is my current level. So I am saying that the maximum which I have traversed is smaller than what currently I am standing at. Current level is greater than maximum which I had traversed in the past, right? So at that time, whatever is the node I am encountering will be inside my answer. I'll be putting it inside my answer list. Is it clear? Yes or no in the chat box? I'm new to coding. Please guide me. Okay. So there's a reply from Abhinav. Okay, so thank you for the confirmation. So now I'll be traversing it in this manner, in pre-order traversal. Okay, so currently my level is 1 and currently maximum level is 0. So I can see currently I'm standing at a higher level. Okay, and which is the node currently I'm standing at 1. So I'll be adding it inside my answer list and I can observe this condition to be true. So now moving on forward and I'll be exploring the right hand side first rather than exploring the left hand side. So now currently, and whenever I am moving towards a new level, I'll be updating my level as well, right? So currently I was at level 1, so now I am traversing to one of the child node, right? So I'll be increasing the level by 1, so now level will be equivalent to 2. And whenever I have encountered this condition that max level is lesser than your current level, I'll be updating as well. So just let me go back, rewind a bit, and get back to you guys. So currently I'm starting from the first. I'm starting from beginning. Okay, so currently my max level is 0 and your level is equivalent to 1. I'm standing at this node. I'm standing at node number 1. I can see this condition is true. So what I'll be doing, I will be updating the maximum level to whatever is the level. I can see this is going to be my new level, and I'll be adding the current node to our answer. So 1 will be added. So now exploring the right hand side first. So increasing the level by 1. So level will be equivalent to 2. And I can see this condition to be true again, that 1 is lesser than 2. That means a new level has been encountered. And this is the node which has been encountered for the first time. And this is the first node, right? So I'll be adding it to the answer as well. So 3 will be added. So again moving towards the right hand side. And before moving towards the right hand side, I need to update this maximum level as well. So maximum level will be equivalent to 2. So now moving towards the right hand side, 7 is the node and level will be increased by 1. So now level is equivalent to 3. And I can see maximum level to be lesser than current level. Okay, so updating first of all the maximum level and putting this node 7 inside my answer list. So 7 will be present over here, right? And now again trying towards the right hand side, but nothing is present over here. So let's explore the left subtree. Nothing is present over here. So trace back. So trace back. So as I'm tracing back, so currently I'll be standing at this node, right? As I'll be going back, I'll be now standing at the node number 3. So my level will be decreased by, because currently this is level number 2, this is level number 3, and this is level number 4. This is level 1. Okay, so now your level has decreased by 1 because you have backtracked, right? But your maximum level remains as it is. So from this node, I'll be exploring the left subtree. Okay, and as I'm moving towards the left subtree, level will be increased by 1, so 3. And I cannot see this condition to be true again, so nothing will be added to my answer list. So from here, I cannot move forward. So again, backtrack. So backtracking, and this node has been explored. Both its left and right child have been explored, right? So coming back to this node, so this is at level number 1. So currently what is your level? My level is equivalent to 1, not 3 or 2, right? So currently I am standing at level number 1. So now from here I'll be exploring the left subtree. So now your level will be increased by 2. This is 2. And can you see this condition 3 lesser than 2 to be true? No, not true. So nothing will be added. Now moving towards the right subtree, level will be increased by 1. So 3. And what is maximum level and current level? So I can see 3 is not lesser than 3. So this node will not be added. From here I cannot move anything anywhere forward, right? So again I'll be backtracking. So again I will be backtracking, and currently I'm standing at this node. So now I need to explore its left subtree. So over here the level is equivalent to 3, and now moving forward exploring the right subtree. So level will be increased by 1. So now your level is 4 and your maximum level which you encountered is lesser than your current level. So first of all, update the maximum level and put this node inside your answer list. So 8 will be present. Okay. And so now from here, can you move anywhere else? No, I cannot explore the left or the right child, right? So I'll be backtracking again. So currently I'm standing at this node. From here I cannot move in this direction, so again backtracking, and hence at the end you will be ending up at the root node. So you have explored the entire binary tree, and this is what you got. I got 1378 as my nodes from the right view. Okay, so basically this is a recursive approach, and the key point of this approach is that whenever whenever you encounter a new level, current node is in the right view. Is in the right view of the binary tree. Okay, so this is the point, and this condition will give you the nodes that are visible from the right hand side. Is it clear? Yes or no in the chat box? Any doubt, then post it in the chat box. I'll clear all your doubts, or else we'll be moving on forward. So at least I need a reply from you guys whether this is clear or not. Yes, recursively go to the right and left and add visited level to hash table and print non-visited values. Okay. Practice is the key for coding success. Yes, exactly. Okay, so now I guess I can write down an algorithm for this. Basically, I'll be using a pre-order traversal. Okay, so over here you will not be doing anything for the root node except this condition. For the root node, you will be checking this condition. Okay, and if this condition is satisfied, then add it to the answer list, right? So I'll be writing down the algorithm so that you guys can code in any language you want, right? Okay, so I'll be using a recursive function. So let's say this is my function, and the argument passed to this is nothing but the root and your current level. Your current level. And let's say I have a maximum level variable which is going to be accessible globally, and currently it will be equivalent to 0. And I have an answer list, or let's say there is an list available which will be available globally, so that you can put the nodes inside this list. Okay, so basically we have two global variables. So now basically first of all what you will be doing, D, R and L. So encountering the root means that if you encounter the new level, if your current level is the new level, that means your maximum level value will be lesser than your current level. If this is the condition, that means you have encountered a root node. Basically that root node needs to be added to your answer list. So what I'll be doing, I'll be adding, let's say I'm calling it as answer list, and I'll be adding the current nodes, let's say value, current nodes data to your answer list. An answer list is only going to store the integer values. Okay, how is the approach more efficient than BFS1? Okay, so for BFS, you needed the queue data structure, right? And basically, in the queue data structure, you can expect the time complexity to be equivalent to order of n. Okay, near about order of n. And let's say, see, in this binary tree, this is a binary tree, right? You guys agree? So if I was using BFS algorithm, no. See, in BFS, what you will be storing at any instant, how many nodes can be possible? At any instance, the number of nodes that will be possible will be equivalent to the maximum nodes. Like let's say at any level, there are uh, let's say m number of nodes. Okay, at some level there are m number of nodes, and this is the maximum number of nodes at any level. And what is the height of this binary tree? What is the height? 1, 2, 3, 4, and 5. Right, the height is equivalent to, let's say, 1, 2, 3, 4 and 5. So height is equivalent to 5, and how many nodes are present at this level? 1, 2, 3, 4, 5, 6, 7, and 8. 8 nodes are present. So basically, the height is obviously smaller than the number of nodes at any level. So basically, the space occupied by the queue will be greater than the height of the tree. Over here, as I will be using the recursive approach, the recursive stack will be occupying the space equivalent to the height at any worst case, right? While if I was using the queue data structure, then this is going to be the difference in the space occupied. I hope this makes clear. So basically, this is going to be around 2 to the power 5 or something. Yes, over here there is one node, 2 to the power 0, 2 to the power 1, 2 to the power 2, and 3, and let's say this is 4. So basically, this is the maximum number of, let's say, 2 to the power h minus 1. This many nodes can be possible, and this is the space that will be occupied by a queue, while h is the space you will be using in your recursive approach. Like in case of skewed binary trees. In case of skewed binary trees, both of them will be equal, right? So height and see, in the skewed binary tree, yeah, that approach will take, in worst case, only a single element will be there inside your queue, like at any instant. But this is the worst case in which this approach will be occupying the highest space. Okay. Although if you consider this scenario, no, then in your recursive approach, the space will be equivalent to order of h in any of the scenario. Okay. But in your BFS approach, in worst case, this is what your queue will be uh, like handling at any instant. In worst case, 2 to the power h minus 1. Okay. Okay, Rishit. So now, if I'm encountering the, let's say, current node, and if this is the condition, that means a new level has been encountered, I'll be adding the root node to my answer. And then what I'll be doing, I'll be updating your maximum level. That, okay, I have encountered a new maximum level. So this is going to be my new maximum level. Okay. And now exploring the right subtree and the left subtree. So calling the right subtree. The reason for exploring right subtree before left subtree is that I need a right view. Okay, that is the reason. So I'll be exploring the right, and I'll be increasing my level by 1, because I'll be going towards a new level, right? And after exploring the right subtree, explore the left subtree. Exploring both the trees is very important, because you can encounter this kind of scenario as well. Over here you can observe that if you are not exploring the left subtree, no, you will not be able to find this nodes, right? So exploring the left subtree is also important. You cannot discard any of the nodes. Okay. And the base condition is that the current node is equivalent to null. If the root node is equal to null, as this function is not going to return anything, this is a utility function, okay, a helper function which I have created, and this will not return anything. And this is the entire logic. Basic traversal technique is used, and two different variables are required. One variable is handling the maximum level encountered, and the other variable is handling the answer, right? I hope this was clear to everyone. So now we can move forward towards the coding implementation part. If you have any doubt, just post it in the chat box. Okay, so I need two global variables. So let's say one of the variable is maximum level, and maximum level encountered will be initial equivalent to 0, and I'll be using one more uh, global variable, that will be the answer list. So I'm using an answer array list, because the return type of this function is going to be a list. So now I'll be creating a helper function. So I'll be calling that function as fun, and I'll be passing the current level as level number 1, and These are the initial arguments, and at the end of this function, I'll be returning the answer list. So this function, void function, what will be its logic? Node root, and I'll be using one more variable, level variable. So, and this is going to be our initial condition. If the root is equal to null, just return from at this point. And if your maximum level is lesser than your current level, then that means a new level has been encountered. So adding the current node to the answer and updating your maximum level. Java. Okay, and I'll be exploring the right subtree, increasing the level by 1, and then exploring the left subtree, increasing the level by 1. And that's it. So let me erase this comments. Okay, and let's try to compile and run. Any doubt till now? Yes or no in the chat box, and if you have any kind of doubt. Okay, so compilation was completed, and let's try to submit it. Okay, so basically the time complexity of this approach remains order of n, but the space complexity in all the scenarios is going to be order of h, not more than that, not less than that. Okay, so this is the solution, the optimal solution, and I'll be sharing the link for this solution in the chat box as well. So if you have any doubt in the explanation part or any of the part, just write down in the chat box, or else write down no doubt or anything, just to indicate. Okay, just give me a minute, I'll be sharing it. Okay, thank you for the confirmation, everyone. Okay, so here is your solution, which we just saw right now. Okay, so that was it for today's session. If you really enjoyed, then do hit the like button, share it with your friends, and to watch such an interesting to watch interesting content like this one, then do subscribe to Geeks for Geeks channel. Right, clear cut. Oh, thank you, 007. Okay, so bye bye, good night, and best of luck for the upcoming problem of the day.